So we're looking at rules of radicals. And we just did our warm-ups. We're looking at how to, when do we have to rationalize the denominator?
When they don't go into each other.
Our rules for division were very clear. It was if the denominator is a perfect square, break it down. If the, or take the square root. If it's not, try to simplify the fraction. Maybe your denominator goes away. But what do we do when it doesn't, like in the examples that are in green here? Well, of course, technology is not going to work. So I'll have to do this. All right, so what we need to make a note of is that the reason we would do this is that you cannot have a radical, or you can't have a fraction under a radical. So no fractions under the radical. No fractions under the radical. In our final answer, and no radical in the D. So you can't have a fraction under, or you can't have a big fraction under a radical sign, or a radical symbol, and you can't have a radical in the denominator. And so if you can't just take the square root of the denominator or reduce the fraction, and you still have that radical in the denominator, then we have to do something special. Okay? So in the next box, the example, I'm going to make a note that b over a, it's not evenly divisible, so it does not equal an integer. Does anyone remember what an integer is? Your positive counting numbers, 0, and the opposites of the counting numbers. So it's not an integer. It's going to remain a fraction. So if I could divide it, I would. Then I wouldn't have a denominator. But I can't divide it because it's not an integer. And apparently I spelled it wrong. It should be an E between the T and the G. Also, a is not a perfect square. Because if it was a perfect square, I would just take the square root of the denominator and not have to worry about having a radical down there. If that's the case, then we have the following that we have to do. We start with the square root of b over the square root of a. What do I multiply the top and bottom by? Square root of a on both of those. So the top becomes the square root of ab, or a times b, their product. And what's the denominator become? A, that's correct. Because that's really the square root of a squared. And square root and squaring are inverse operations. So there's the rule with in variable form. We're going to try this for 2 problems, and we're going to look at some of the problems in our notes for you to try. So our first one here in green, square root of 5 over square root of 3. 3 is not a perfect square, so I can't just take its square root. 3 will not go into 5, so I can't just reduce the fraction. Always try to do that first. Since I can't do that, I'm going to multiply the denominator by the square root of 3 in order to get rid of that radical, because the square root of 3 squared is just 3. And my numerator then becomes the square root of the product of 3 and 5, which is 15. So square root of 15 over 3. I would check to see if I could break down the 15, but the only numbers that go into 15 are 5 and 3. Those are both prime. They're not perfect squares. So I'm done. The square root of 12 over 5. 5 is not a perfect square, so I can't take the square root. 5 does not go into 12 evenly, so I can't reduce the fraction. So now I have to rationalize the denominator. By multiplying the top and bottom by the square root of 5, I get the square root of 60 on top, and I get 5 in the denominator. Well, I've cleared the denominator of the radical, so I don't have any radicals in the D, in the denominator, which is good. but the square root of 60 needs to be broken down. What perfect square will go into 60? Anyone?
4.
4. 4 by 15, right? So the square root of 60 is really square root of 4 by square root of 15, which is 2 square roots of 15, and I put that over 5. Now, if 2/5 could be reduced, the numbers that are outside the radical, I would try to reduce them, but they can't be. Square root of 15 won't break down anymore because no perfect squares go into it, and I can't divide it by the 5 because they're not both under a radical. To divide things with a radical, they both have to be under the same type of radical. So that's it for the examples on our radicals flipper. Now we're going to go to the notes. And I believe this is on the 3rd page of your notes. We're not going to do the Explorer. We kind of did that as our warm-up today. So I'd like you to try letters A through D. What should you always try to do first if possible? Simplify, yes. First, if it's a perfect square, well, that's easier to do. If it's not, try to simplify. Just take a second to try those problems. Raise your hand if you have an answer for letter A.
I don't.
4 or 5, oh, more people, this is better. This is looking better, even more hands. All right, Quaid, what'd you get, sir?
I get the square root of 23, and I get 5.
I think you meant the square root of 35 over 5, yes. Any questions on letter A? That was exactly like the first example we looked at. The other ones are a little different, we'll look at them, but 5 doesn't go, or 35 can't be broken down by perfect squares. I can't divide it by 5 because the 5 is not under a radical. That's the answer. Letter B. What don't I like in this problem? What definitely has to get addressed that right now can't simplify? Nick?
There's a radical underneath the
in the D?
Yeah, the denominator.
There's a radical in the D. No radicals in the D. It's not a political joke. All right, we got to multiply the denominator and numerator by the square root of 7, which is going to give us a very large number. 3 square roots of 560, right? Yes. All over, well, what's square root of 7 times square root of 7? 7, but there was a 5 multiplied under there, so that's going to be over 35. So we're good so far, and 3 over 35 doesn't reduce, but we do have to check our radicand, which right now is 560, and take out all perfect square factors that we can. We're going to see if we can find the largest one. Did anyone find the largest one, they think? 16. 16 does go into it 35 times. So I'm just going to break this down over here. It's 16 by 35. Will any perfect squares go in the 35? No. So then we found the largest perfect square. If we didn't find the largest, we could just pull 1 out that we know, like 4. But then we'd have to break down the radical again. Yes?
I did it differently. I separated the fraction into 3/5 times the square root of 8 divided by square root of 7.
And you can do it that way, and that's okay. That'll still work. So this is 4 square roots of 35. This right here is 4 square roots of 35. What do I do with the 3 in front of it? Times it. So what is 3 times 4? 12. So that's 12 square roots of 35 over 35, and 12 35ths cannot be reduced because the only common factor is 1. Any questions on letter B? Yes, sir.
So when you got the squares of 35, you have to take 560 and then divide that by 3 or something?
I divided it by perfect squares, and the largest perfect square that went into it was 16. That's where the 35 came from. This was 560. Factors of 560, one of them being the perfect square is 16, the other one's 35. 16 times 35 is 560.
Okay, I get it.
All right, letter D. There's two ways to do letter D. Actually, the very first thing you have to do for letter D is simplify, not stupefy.
Letter C.
Square root of 13, although some of you might have felt stupefied, over the square root of 20. So I do what? Well, 40 won't go into 26. Or I could. You can. You'll get a bigger number and you have to reduce it. It'll work. It'll just be messier to reduce. We should always try to reduce first because sometimes that leaves our denominator as a perfect square. In this case, it does not. We could break down the 20 if we want to, or we could break it down at the end. What do you guys want to do? Now, if you want it broken down now, raise your hand. Okay, my other classes didn't want that. Most of you do. Square root of 20, the reason they did it at the end was they're like, well, I have to multiply to clear the radical anyhow, but this is okay. 20 is 4 by 5, which would give us 2 square roots of 5, right? So we've got, this becomes square root of 13 over 2 square roots of 5. Questions on where that came from? Andrew.
So I multiplied it by the square root of 40 and I got square root of 1040 over 40. And then I divided it by 40 and got square root of 26 over 1.
I'll have to look at it. So the way you started it is okay. I'm not sure if you broke down the number correctly. So how am I going to rationalize this? What part of this denominator has to be rationalized? Not the whole denominator. The radical part, square root of 5. So I'm going to multiply at the top and bottom by the square root of 5. 13 by 5, both are prime, is going to give me 65, which does not have a perfect square going to it. And then this becomes 5 times 2 is 10. So if you ended up with the square root of 65 over 10, doing it another way, you're okay. If not, I'll need to look at yours to figure out what you may have messed up with. Even if I multiplied by square root of 20 on top and bottom, I'd still be breaking it down and simplifying the fraction. I should still get this same answer. We'll take a look at D, and then I'll come by and see if I can help some of you if you didn't get that correct. Letter D. What goes into both of those parts of the fraction? 5. So this is the square root of 25. Yay, I'm happy. That's a perfect square. There's my numerator. It's 5. The denominator, unfortunately, is now the square root of 7. Can I leave it like that? No. So I'm going to multiply the numerator and the denominator by square roots of 7 to get 5 square roots of 7 over 7. Questions on that? All right. Before we do the next thing, actually, as the next thing that I'm going to ask you to do, and I'll come back, some of you are still struggling with that, you're going to go to the second page. At the bottom of the second page, it says explore, and it says, can I add or subtract these things? And so, if you can, go ahead and do them, okay? And then see if you can figure out why you can versus why you can't. And if you're struggling or struggled with the last one or two, let me know. I'll come by and check. Tyler, what'd you get?
12x squared.
12x squared is correct, or 12, nope, just 12x. Just 12x. We're not multiplying, we're just combining, adding them together.
What if there's, oh.
I have 3 and I have 9, so in total I have 12. Letter B. Who has an answer for letter B? Yes.
4y squared.
4y squared. What's the only other problem I can actually combine on this page? You can shout it out. E. And so that is 8 square roots of 2. Because I have 5 of them on the left and 3 of them on the right. So in total, I have 8 of them. So what are we doing for these? Why can't I put the other ones together? Mr. Schmidt.
Because like my 8th grade math teacher says they have like different last names.
Okay, yep, different last names. We said that they had to have the same variable to the same exponent. So if I gave you the square root of x and the cubed root of x, do those have the same exponent? No, so you can't put them together. Okay, but these do. They have the same not necessarily variable, but same base. They both have a radicand of 2, which is a base if we think about it exponentially, and the same root, which is an exponent of 1/2. So we can put them together. You can't put these together because they don't have the same last name as you put it. They have different bases. Same exponent, different bases. These have different bases. Can't put them together. These have different exponents. Can't put them together. It's combining like terms. So if we go to our radicals flipper, we'll talk about addition and subtraction of the root. Our goal is to combine like terms, but they must have the same root and the same radicand. Must, that's not working. Must have same root, so they can't, one can't be a square root and the other one be a cube root. Must have the same root and same radicand. So that's like the square root of a plus the square root of a minus the square root of b would become 2 of the square root of a minus the square root of b. I can't combine those two because they don't, even though they have the same root, square root, they don't have the same radicand. Give the problems in blue and red a try. Well, give the blue problem a try. You should be able to get the answer for the blue problems. We'll talk about the red in a second. The example, the blue example. Yes?
So, this is kind of like the answer, but like,
That's, you don't have to write it. Nope. How many square roots of 5 do I have after I subtract those?
One
I have 1 square root of 5, which I can just write as the square root of 5. I don't have to put the 1, it's hidden in multiplication. I can if I really want to. And I have the square root of 5 plus the square root of 6. Is that going to give me the square root of 11?
No.
Or the square root of 30?
No.
When would it give me the square root of 30? If they were multiplied, but it's a plus sign, so I don't do that. All I am doing is combining like terms. As it's written right now, is the red problem, are those like terms?
No.
Could either of those be simplified?
Yes.
The square root of 18 can become the square root of 9 times the square root of 2, using the product rule, breaking down the factors, which is really 3 square roots of 2. And we had a 3 in front of it. So is that going to be 6 square roots of 2 or 9 square roots of 2? It's going to be 9 square roots of 2 because we have 3 times 3. So now I've got 9 square roots of 2 minus 2 square roots of 2. Can they be combined now?
Yeah.
Yes, because now they are like terms. That gives me a total of 7 of the square root of 2. 7 square roots of 2. Questions? So it gives us a couple examples in our flipper. So we're going to go back to this, and there are some problems right there for you to try. Right under the ones that you had just tried with combining like terms. There are answers for A, B, and C. You're just combining like terms. All right, we're looking now at what we didn't talk about. I'm not going to worry about it in the flipper because we already talked about the product rule. But we're going to go to the top of the 3rd page of your notes, which is the last page, the top of it. We've already done some like this, but it wasn't on our elephant riddle or any of that common practice stuff, but where we had these multiplied. So how many things are multiplied here? How many expressions do I really have in letter A? 4 expressions. I mean, I kind of have 2, but it's because they're grouped. It's all multiplication. So this is really 4 times square root of 3 times 3 times square root of 12. It's all multiplication. So all I need to do is group the terms together that I can actually multiply. I can't multiply my 4 with my 12 because one of them has a radical and the other one doesn't. But my 4 and my 3 could be multiplied together to give me 12. And my square root of 3 and my square root of 12 could be multiplied together to give me square root of 36. And I have to break down the square root of 36. So 12 times 6 is 72. So all we're doing for these problems is regrouping the numbers that we're multiplying together. So try this for letter B.
Wow. Oh my.
All right, so which numbers can I actually multiply together? 3, the negative 2, that's it for like those, right? So that's negative 6. And then the square root of 8, the square root of 14, the square root of 6. What is 8 by 14 by 6?
672.
So it's negative 6 square root of 672. Oh boy, that looks like fun. What's the largest perfect square that you found to go into 672? I think it is 4. 4 times what? Is it 16? 16 goes in how many times? How many times?
42.
42 times. So 672 is really the square root of 16 times the square root of 42. 42's divisors would be 7 and 6, or 7, 3, and 2. Those are the prime numbers. We don't have any that would, no perfect squares will go into 42. So this is 4 square roots of 42, and there's a negative 6 multiplied in front. So negative 24 square roots of 42 is the final answer.
Okay. We have some more time for C and D.
Now there are 2 ways to do letter C. I'm going to show you the most common way first. The most common way to do letter C first, and if you struggled with B, I'll come back and check your work in a second. It is squared. What does squared mean? It means I have how many factors? 2. So I really have, this is really 2 square roots of 24 times 2 square roots of 24, which I could group together and get 4 times 24, because square root of 24 squared is 24. And 4 times 24 is 96. That's one way to do this problem. The other way to do this problem is to treat it as an exponents problem. You have an exponent on top of exponents. What's the exponent on the 2?
1.
This is really 2 to the first. Well, it will be 2.
Oh, okay.
What's the exponent on the 24? If it's the square root, what exponent is that? 1/2. And then I have a 2 on top. What do I do when I have an exponent on top of exponents? Multiply it by the exponents, not the bases. So that would become 2 squared times 24 to the first, which again is 4 times 24, or 96. So you have 2 ways of looking at that. You can choose which one makes more sense or is more efficient for you to get the answer quickly. Yes, ma'am.
So when multiplying the exponents, that takes away the radical because you're kind of.
When you have, yes, the square root of a times the square root of a is the square root of a squared, right?
Yeah.
And square root and squaring are inverse operations. Or put another way, this is a to the 2 over 2, which is a to the first. So they undo each other. All right. Well, we're going to jump to the going over questions from last night's riddle. However, if you don't have questions from last night's riddle, you can start on the day 2 practice.